The JK flip-flop overcomes the issue that the RS has in the sense that it overcomes the illegal state of the RS flip-flop. So the JK flip-flop again comes in two types of configurations. You've got the positive edge trigger and the negative edge trigger. Now both symbols are very similar. That indicates the clock, and then we've got Q and not Q on the output. This is my positive edge triggered JK flip-flop. The negative edge trigger, again JK with a CLK clock in the middle, that feeds into that not symbol over there, same as we had with the RS flip-flop. Then we've got Q and not Q on the output. Now in order to obtain that, the clock feeds into the NAND that we've looked at with that feedback. Now how this works is there's a slew rate, a time that it takes the transistors inside this NAND to actually switch over there. Because there's a 0 there, that becomes a 1 on the output, and that 1 feeds back. So the moment this now becomes a 1, for a short duration, that 1 is equal, and that 1 will turn this NAND off. Then that 0 feeds back in there, which will turn that on. So it is a very quick successive cycle that we have with the JK. This is the negative edge triggered JK flip-flop. Now the operation is exactly the same. A 1 will switch, a 0 will switch depending on what the other inputs are for the NAND gates. I'm going to draw this large so that we can clearly see what is going on with the JK flip-flop. So the J, the clock, and the K. The J feeds into a 3 input NAND. The clock feeds into that NAND, and the K also feeds into a 3 input NAND. This clock feeds in to that NAND over there. From here it's going to go into another NAND, and there we're going to have another NAND which is going to feed into that NAND over there from the K. Now this is going to be my not Q, and that's going to be my Q, and like we had with the RS, we're going to have that zigzag configuration over there, and we're going to have that zigzag configuration that we had, same as with the RS flip-flop over there. But now this point, this feedback loop feeds back into the J NAND, and the K NAND feeds back into the Q's output over there. So that's not Q. Now we're going to color code these. In order for this to operate, we already need a starting point condition. So let's say that Q is 0 and not Q is 1. That puts it in the reset, or it is currently in the reset state. what would have caused that is a 1 and a 0. Sorry, a 0 on the J and a 1 on the K. So I'm now going to put it into the set mode. So I'm going to put a 1 on J and I'm going to put a 0 on K. Okay, because we're working with NANDs, whenever there's a 0 on the N, then 1 will be seen on the out. So a 0 goes in, so this already turns into a 1. This 1 feeds in there. This 0 feeds in there. And it also feeds in there. This 1 feeds in there, and it feeds in, sorry, that is a 1. Okay. Now the moment I receive a clock pulse, that's a 0. The moment I receive a clock pulse, these go high. As they go high, this was 0, and that was 1. So now I've got 3 1s, that becomes a 1, knotted, turns that into a 0. This 0 and that 1 turns this Q into a 1. Okay, this 1 is now going to feed into that position there, and that 1 is going to feed into that position there. So that 1 and that 1 converts this not Q into a 0, and that is my set state. When I remove the clock pulse, those become 0s, which turns those both into 1s, which means these outputs stay in their current condition. That 0 feeds back into there. And that 1 feeds into there. I've got that. Okay. Now, if I want to manually put it in the hold condition, I put 0s on my inputs at J and K. That 0 causes the AND to go low, knotted, converts that 0 into a 1. That 0 causes this one to stay 1. 1 and 1 on the inputs over there, so that's now 1. That 0 and that 1 turns that 1, forces it to stay 1. This 1 feeds back into there, which causes that one to stay in the 0 state. So that is my hold state. Let's quickly draw the truth table. J, K, and my clock input. Q versus not Q. So those are 0s. 1, 1, 0, 1, 1, and then irrespective of what happens, if that is a 0 on the clock, Q and not Q stays what they are. That's my hold state. We've seen that if I have a 1 and J and K, then I still have Q and not Q, which is a second hold state. And we've seen that if I've got a set condition, that was the blue, that was the red. The blue caused a 1 on Q and a 0 on not Q. That was my set. Now we're going to look at 0, 1 condition. That's my reset. Let's go purple. So 0 on J, 1 on K. That 1 still feeds back there. That 0 still feeds back there. So now this 0 feeds in there. This 1 feeds in there. So that 1 and that 0 and that 0 causes this to be 1. these are all three ones, which makes that a 0. So the 0 and the 1 causes this to be a 1, and the two ones over there causes this one to be a 0. So that is now my 0, 1, which is my reset state. And here comes the advantage that we've got with the JK. If I apply 1s on both my inputs along with a clock pulse, there we've got a 0, there we've got a 1. So that 1 feeds in there, that 1 also feeds in there. That 0 feeds in there, and it also feeds in there. So when I introduce my clock pulse, 1, 1, 1 turns that into a 0. Here I've got 0, 1, 1, that turns that into a 0. That 0 and that 1 converts this into a 1, and those zeros convert that into a 0. So we can see we've had a toggle condition where the 1, 1 turns the Q into a not Q value and the not Q value into a Q, and we call this our toggle state. And that is the operation of the clocked JK flip-flop.